Think back to your school science class for a moment. You probably saw a colorful diagram of a planet cut in half, looking a bit like a giant jawbreaker candy. This model showed us the basic structure of our world, Earth. It taught us that our planet isn't just a solid ball of rock and dirt. Instead, it's made up of several distinct layers, each with its own special properties. Understanding these layers is the first step to appreciating just how complex and dynamic our home really is. These aren't just static sections. They are constantly interacting, moving and shaping the world we experience on the surface. Let's start from the outside and work our way in. The very top layer, the one we all live on, is called the crust. It's incredibly thin compared to the rest of the planet, like the skin on an apple. Beneath that lies the mantle, a much thicker layer of hot, dense rock that flows very, very slowly over millions of years. This slow-motion churning is what drives the movement of our continents, a process we call plate tectonics. It's the engine behind earthquakes and volcanoes, constantly reshaping the surface of our world in a beautiful, powerful and sometimes destructive dance. Deeper still, we reach the core, which is divided into two parts. First is the outer core, a swirling ocean of molten iron and nickel. This liquid metal is super hot, and its constant motion is incredibly important. As this metallic fluid churns and flows, it generates a powerful magnetic field that extends far out into space, acting like a protective shield. This magnetic field, a direct result of the outer core's activity, deflects harmful solar radiation from the sun, making it possible for life to thrive on our planet. Without it, our atmosphere would be stripped away, and we wouldn't be here. Finally, at the very center of it all, we have the inner core. For decades, we believed this was the final stop on our journey to the planet's heart. Scientists determined it was a solid ball of iron and nickel, squeezed under immense pressure, and heated to temperatures as hot as the surface of the sun. The pressure is so great that even though it's incredibly hot, the iron can't melt. It's forced to be a solid. For a long time, this four-layer model, crust, mantle, outer core, and inner core, was the accepted story of our planet's interior. So, how do we know what's happening thousands of kilometers beneath our feet? We can't exactly drill a hole to the center of the Earth. The heat and pressure are far too extreme for any of our current technology to handle. Instead, scientists have become planetary detectives, using a clever technique to listen to the Earth's deepest secrets. They use the power of earthquakes. When an earthquake happens, it doesn't just shake the ground where it occurs, it sends powerful shock waves, called seismic waves, rippling through the entire planet. These waves are like a planetary-scale ultrasound. These seismic waves travel from the earthquake's origin through all the different layers and are then picked up by sensitive detectors called seismographs all around the globe. By studying how these waves behave, scientists can piece together a picture of the planet's interior. The waves change speed and direction as they pass through materials of different densities and states, solid, liquid, or something in between. For example, some waves can't travel through the liquid outer core at all, which is how we first figured out that part of the core was molten. It's a brilliant way to see the unseen. For this latest amazing discovery, scientists took this idea to a whole new level. A team of researchers, including some brilliant minds from the Australian National University, gathered a massive amount of data. They looked at seismic wave readings from thousands of earthquakes that had been recorded over decades by a global network of monitoring stations. They were specifically interested in the waves that traveled straight through the planet's center and back out the other side. They wanted to know if these waves could tell us something new about the inner core itself, a place of unimaginable extremes. Using powerful computer algorithms, they analyzed how these waves changed as they passed through the very heart of the Earth. They noticed something fascinating. The waves that traveled directly through the center moved at a slightly different speed compared to waves that just skimmed the inner core. It was a subtle difference, but it was consistent. This variation suggested that the very center of the inner core was not the same as its outer parts. It was evidence pointing to a new boundary, a new layer, hidden deep within the solid inner core. It was like discovering a pit inside the pit of a peach. This newly detected layer has been nicknamed the inner core. It's a solid metallic ball, about 1,350 kilometers in diameter, nestled inside the larger inner core. So what makes it different? It's not about a change from solid to liquid. like the boundary between the inner and outer cores. Both the inner core and the inner core are solid balls of iron and nickel. The difference, scientists believe, lies in the structure of the iron crystals themselves. Think of it like looking at the grain of a piece of wood. You can have two pieces of the same wood, but the grain can run in different directions. In the outer part of the inner core, the iron crystals seem to be aligned in one direction. However, in this newly found inner core, the crystal structure appears to be arranged differently, perhaps oriented at a different angle. This structural change creates what scientists call anisotropy. It's a fancy word that just means a material has different properties depending on the direction you measure it. Because of this different crystal alignment, seismic waves travel through the inner core at a different speed depending on the path they take. This is the key clue that lets scientists know they were looking at something distinct. This discovery is a huge deal because it suggests that the formation of our planet's core was more complex than we ever imagined. The existence of two distinct solid layers within the inner core points to the possibility that there were two separate, significant cooling events in Earth's very early history. Imagine the core slowly solidifying from the center outwards. A major global event could have happened, changing the conditions and causing the crystals to start forming in a new way. This new layer is like a fossilized record of a dramatic event that shaped our planet billions of years ago. Furthermore, understanding the structure of the entire core is vital for understanding Earth's magnetic field. This field is generated by the churning liquid outer core, but the solid inner core plays a crucial role in shaping and stabilizing it. A more complex layered inner core could have profound implications for how the magnetic field has evolved over geologic time. It might help explain why the magnetic poles have flipped in the past and give us clues about the field's future behavior. This isn't just an abstract geological finding. It's a piece of the puzzle that explains how our planet works and remains habitable. This revelation that Earth has a fifth layer fundamentally changes how we think about our planet's formation and evolution. It's like finding a previously unknown chapter in Earth's autobiography, right at the very beginning of the book. The idea that a major event in our planet's distant past was significant enough to alter the growth of the core is mind-blowing. It opens up a whole new line of questioning for geologists and planetary scientists. What could this event have been? Was it a massive asteroid impact or a change in the planet's internal cooling process? The inner core holds the clues. Studying this new layer could help us build a more accurate timeline of our planet's history. By modeling how and when these different core layers formed, we can better understand the conditions of the early Earth. This, in turn, informs our understanding of how life began and evolved. Every new detail we learn about our planet's deep past helps us connect the dots between geology, chemistry, and biology. This discovery could even help us as we search for habitable planets elsewhere in the universe, giving us new insights into what makes a rocky planet like ours come alive. Of course, this is just the beginning of the journey. While the evidence for the inner core is strong, it's based on models and data that have some limitations. For instance, we have fewer seismic monitoring stations near the North and South poles, creating gaps in our global data. Future research will focus on gathering more detailed seismic information from these regions to confirm and refine our understanding of this deep, hidden layer. Scientists will be working for years, if not decades, to fully map out its properties and unlock the full story it has to tell us about our planet's dramatic past. Ultimately, the discovery of the inner core is a beautiful reminder that our planet is still full of surprises. Even after centuries of scientific exploration, there are fundamental things about our own world that we are just beginning to understand. It shows that science is not a collection of settled facts, but a continuous process of discovery, questioning, and wonder. There are still mountains taller than Everest at the core mantle boundary, and vast, mysterious zones we are just starting to map. The Earth is a complex, dynamic, and endlessly fascinating place, and there are so many more secrets waiting to be uncovered right beneath our feet.